Welcome back, everyone. In the last segment, we learned about properties of sigma notation, and we used that to tackle the concept of approximating area under a curve. And we used a rather lengthy method that consisted of summing areas of rectangles and letting the number of rectangles approach to infinity to find the area under the curve. So in this segment, we're going to do this finding exact area under the curve, but with an easier method known as the fundamental theorem of calculus. Just to summarize what we've been doing, so we had a function f of x, and we're trying to find the area from a to b under that function f of x, and we formed n rectangles under it. And typically we use partition points, like let's say point A being the left-hand side. So you may call this point x sub 1, x sub 2, x sub 3. Typically we had like 1 over n, 2 over n, 3 over n, and so forth. And the base of each rectangle, we can call them delta x. And the area of each rectangle was base times height, right? So if the base is delta x, in the last segment, that might have been 1 over n or 2 over n, depending on the problem, etc. So here it's going to be delta x, and the height is when you plug the x sub 1 into the function. Your function is the f of x function. So it is f of x sub I multiplied by delta x. This is the area of one rectangle. If you sum it up from 1 to n, you have the areas of n rectangles. And to find the exact area, we had to take a limit as n goes to infinity of the quantity above. So limit as n goes to infinity of a sub n. And basically what you see right here, we're going to introduce a shortcut notation now. Instead of using limit of a sum, we're going to use the elongated s notation, known as the integral notation, to represent this entire quantity. And so instead of f of x sub I, we write f of x. Instead of delta x, we write dx. So just know that this quantity, integral from a to b, represents the area between f of x and the x-axis over the interval from a to b for positive functions. Okay, now the question is, how do you evaluate that? Because in the past, we evaluated it with some cumbersome techniques. So here we go, the introduction of the theorem that will bring us the shortcut rules. This is what it says, and it's named after Leibniz and Newton, who are believed to contribute to the discovery of this famous theorem. So if you are trying to find the area from a to b of function f of x dx, assuming f is a positive function, then what you need to do is first find the entire derivative capital F of x. And then into the entire derivative, you substitute the upper limit. And then minus into the entire derivative, you substitute the lower limit. You simplify the answer. And this is supposed to give you the exact area under the curve. Very unexpected. There is no rectangles here. There's no summation notation here. So it's really a phenomenal result. And let's take a look at the example we did in the last segment was f of x equals x squared over 0 to 1. We did it with the lengthy procedure. Let's apply the rule, the fundamental theorem to this. Okay, so if you just take, based on this, you want to find the area under x squared from 0 to 1. And typically we put f of x dx. So f of x is x squared dx. It's just a notation, really. It's reminiscent of the times when this represents the height of each rectangle. This represents the base of each rectangle. But the theorem is very specific. It says just find capital F function, which is the entire derivative of x squared, and evaluate this from 0 to 1. And it tells us first plug in the upper limit, which is 1. So 1 to the 3 is 1. So you're going to get 1/3. Minus, it says now plug in the lower limit. The lower limit is 0, so 0 to the 3rd over 3 is 0. So guess what we're getting here? 1/3 minus 0, or 1/3. Phenomenal, amazing result. Gave us the same exact number, but so much easier, right? So we had not done all the other stuff. You may not have appreciated what a incredibly important theorem it is, because it takes a very, very difficult process, tedious, time-consuming. It turns it into a super easy and very, it takes just a matter of seconds when you can calculate the result. Let's do another one, okay? F of x equals x squared over the interval from 1 to 2. How do you find the area under f of x equals x squared from the point 1 to the point 2? So this is the area we're looking for, and we're not going to split into small rectangles and so forth. Instead, applying this fundamental theorem, we're going to integrate the x squared function from 1 to 2. So first take the entire derivative, And then we're going to plug in the limits. This line means we're going to plug them in the next step from 1 to 2. Go ahead and plug in the upper limit first. So 2 to the third will be 8 thirds, 2 to the third over 3, minus plug in the lower limit, 1 to the 3 over 3, or 1/3, and the answer is 7/3. This is the exact area under f of x equals x squared from x equals 1 to x equals to 2. All right, we're going to do a few more examples, and they're going to get a little bit more interesting and challenging as time goes by, but let's enjoy them while they're simple. But even the simple ones, we understand that normally this problem would have been much, much longer, and the fundamental theorem has made it easier through this ingenious work of Newton and Leibniz. All right, let's find the area under x cubed over the interval from 0 to 1. If you have done the group activity, this was the problem I was asking you to do there. We did x squared in class. You were supposed to do x cubed from 0 to 1 using the long method, and you may already know what the answer is there, right? So now let's do it with the short method. From 0 to 1, x cubed dx. So first take the entire derivative of x to the third, x to the 4 over 4, and then plug in the limits, in this case 0 to 1. So we're going to get 1/4 minus 0 over 4, or 0. So the answer is 1 over 4. And if you did that problem the long way, you would have found the same exact answer, 1/4 or 1/4. All right, another example, this one has two terms, integral of x squared plus 2, if you look at the graph. So x squared plus 2 would be a little bit higher. It really goes the other way too, but right now we only want to know the area from 2 to 5. So roughly speaking, a region like this. So same technique. We're going to use the integration technique or the fundamental theorem of calculus. Integrate the function x squared plus 2 dx from 2 to 5. So for this one again, find the antiderivative first and then plug in upper limit minus plug in the lower limit. This may be a good point for you to pause the video for a moment and come back and check your answers. So here is the antiderivative, x cubed over 3 plus 2x. And we're going to plug in limits from 2 to 5. All right, plug in the upper limit of 5. Everywhere you see an x, 5 to the third will be 1/25 over 3 plus 2 times 5, or 10, minus, so by the fundamental theorem, you must subtract. Now plug in the lower limit of 2 into the antiderivative. And we're going to get 8/3 plus 4. And I can distribute my negative sign. I'm going to combine the ones with the fractions first. So I have 1/25 minus 8/3. And then I have plus 10, distributing negative sign, I'm going to have minus 4. So here I have 1/17 plus 6, right? This is 6. And 1/17 seems to be the number divisible by 3 since the sum of the digits is 9, right? So let's find out what is 1/17 over 3. It is 39. So the answer is going to be 39 plus 6, or 45. That's the area under the curve over the given interval. Okay, I will give you a few more examples on finding area under a positive curve. And we will later on in the next class, we will actually take a look at what happens if your function is sometimes positive and sometimes negative. How do you find area in those situations? But for the next few examples, still these are going to be positive regions, the regions that are above the x-axis. So please take a moment to set up this problem, integral of x squared plus 2. Again, we only want it over the region from 0 to 3. So what is the area under f of x equals x squared plus 2 over the region from 0 to 3? So once again, you're going to set up as an integration problem. So evaluate the integral of x squared, or the antiderivative is x cubed over 3. The antiderivative of 2 is 2x, going from 0 to 3. And here we plug in the upper limit minus we plug in the lower limit. to get 27 thirds plus 6 minus 0. So we get 9 plus 6, or 15 is our answer. All right, what about this one? Negative 3x squared plus 12. The area between that function and the x-axis over the interval from -1 to 2. You can get a precise graph if you like using your graphing calculator, but very roughly speaking, this is going to be an upside down parabola. And that goes here as high as 12, so my figure is not up to scale, but I just want to have a general idea about what kind of graph is this, because this technique at the moment only applies when you have a positive function. If it's negative, we have to do something, we have to kind of dissect it, we have to look at in different intervals and then take absolute values of the intervals. At the moment, I just want to confirm that this region is positive, and indeed over the region from -1 to 2, again, my graph is not up to scale, forgive me, but just to give a general idea, this is indeed a graph that is above the x-axis. That's all I want to verify there. So I can apply the fundamental theorem to this function. I'm going to integrate negative 3x squared plus 12 with respect to x, and from -1 to 2. So same technique, right? Take the entire derivative, plug in the upper limit, minus plug in the lower limit. And some of you may be wondering, what's happening to dx when we take the entire derivative? Again, just think of dx as being a symbolic thing. It's there from the days when we're doing summation, notation, and so forth. It's there to remind us that our variable of integration is x, but really it doesn't really do anything. So once you take the entire derivative, it just goes away. And it's also very important to realize that once you take the entire derivative, the integral symbol should go away also. Okay, so don't keep the integral symbol here as you're writing the entire derivative. That would be something wrong. It would not be the correct notation. So here is the entire derivative, negative 3x cubed over 3 plus 12x integrated and evaluated from -1 to 2. And I can simplify negative 3 over 3 is -1. So I have negative x cubed, and plugging in a 2 in there, I'm going to have negative 8 plus plugging in 2 into 12x, I get 24, minus, open another parenthesis, plug in now -1 everywhere you see an x. Now -1 to the third is -1 times another negative is +1, and 12 times -1 is -12. So here I get 16 minus, and then 1 minus 12 is -11. So it really turns out to be 16 plus 11, or 27. So that is the area under the given region, 27. Okay, and then one of them, another problem using a trigonometric function, same technique applies. We want to find area between the function and the x-axis over the interval from 0 to pi over 2. And if you remember the graph of cosine x, roughly speaking, this is pi over 2 right here. And this is 3 pi over 2, but you only want to integrate it from 0 to pi over 2. So this is the only area you would like to get here. So let's integrate our function f of x. As long as it's a positive region, we can do this. From 0 to pi over 2, those are the limits of integration values over the x-axis that we put on our integral limits as a lower limit and the upper limit. And the function that we're going to integrate is 5 times cosine of x dx. All right, so do you remember the entire derivative of cosine function? Which function, when differentiated, gives you cosine? And if you said sine x, bravo, you remember it. Take the 5 out of the integral symbol, it's just a constant, and integral of cosine is sine x, and the limits are going to be 0 to pi over 2. And when you plug in upper limit, you get 5 times sine of pi over 2. And plug in lower limit, you get sine of 0. And what do we know about sine of pi over 2? Does anybody remember? At the top of the unit circle, what is the sine value there? So it is indeed 1, right? And sine of 0 is 0. So our final answer for this question is 5. So To recap what we've been doing so far, we've used fundamental theorem to find a variety of areas under the curve, and this new technique greatly simplified the process to do that. But I want you to know that integration is used even for other situations where you may not be finding area, but you're trying to find something else, and there's going to be many different applications you will see in your mathematical journey if you're taking more calculus classes and beyond. But even in this class, like when we do average value, when we do net change, we're going to need to do integration, not just to find area. And for that reason, I'd like for us to practice integration in general. So if the question says, just find the integral, and without any note about, finding the area, there we don't even have to look at a graph, okay? You don't even have to verify that the graph is positive and above the x-axis and so forth. Just, this is a practice problem on integration. The answer can be even positive or even negative. It's okay. It's just a practice question on integration, and it's not necessarily representing an area, okay? So for these three questions, I would like for you to try to find the integrals. These are known as the definite integrals when you have limits of integration. And please come back and check your answers. Okay, so I hope you had a chance to do these on your own first, and it's not too late. After each one that I do here, please pause the video, try it, and come back and check the answer, because everything looks so much easier when you're watching somebody else do it, right? Like when I watch somebody play basketball or tennis, oh wow, it looks beautiful and easy, but until you do it on your own and you practice and practice, you really are not gaining that skill. So very important to do it on your own as much as you can before you're looking at the solutions, especially once you've seen a couple of the type, you have an idea now how to do them, right? All right, let's try this one. So we're going to take the antiderivative of 6x, which is 6x squared over 2, and antiderivative of 2, which is 2x. Plug in the limits from 1 to 2, but I'm going to do that in a moment. First, let me simplify 6 over 2 here as 3x squared plus 2x, and the limits of integration are from 1 to 2. So at this point, all we have to do is, now that we have the antiderivative, let's just plug the limits. Plug in the upper limit of 2 for x. So you can have 3 times 2 squared, or 3 times 4 plus 4, minus, open another parenthesis, plug in 1 for x. You're going to have 3 times 1, or 3, plus 2 times 1, or 2. So in parenthesis, I would put 3 plus 2. You can then simplify that as 5, and the initial quantity was 3 times 4 plus 4, or 16. So the final answer is 16 minus 5, or 11. So we just did a practice problem on integration. Here's another one. Integrate from -1 to 1 of 3x squared plus 4x minus 2. So take the antiderivative first, right? This one is going to be 3x cubed over 3. The next one is going to be 4x squared over 2, and the last one minus 2x. At this point, simplify 3 over 3. You can cancel those. 4 over 2 is just going to be 2, right? Let's simplify those quantities. And then we have x cubed plus 2x squared minus 2x from -1 to 1. Now you can go ahead and plug in the upper limit minus the lower limit. So take a moment to do that and come back and check your results. So when you plug in the upper limit, you're going to have 1 plus 2 minus 2. When you plug in the lower limit into x to the third, that's -1. So you're going to have, after the minus sign, open a parenthesis, you'll have -1. And then plug in a -1 into the x squared, that's +1, right? So you're not 2 times 1, or 2. And plug in a -1 into the last term, into -2x. That's -2 times -1, or plus 2 again. So now you can simplify this a little bit of arithmetic. I trust that you're going to be able to do that. And the final answer turns out to be -2. All right, another example. This one will take a little bit more careful steps to integrate, like how to integrate square root of x, or how to integrate -5 over x squared, right? So the question is, integrate from 1 to 4 of 3 times the square root of x minus 5 over x squared. My suggestion is first to rewrite both of them. Rewrite 3 times square root of x as 3 times x to the 1/2, and rewrite negative 5 over x squared as negative 5x to the negative 2. So as you integrate 3 times x to the 1/2, keep the 3 as it is, x to the 1/2, you're adding 1 to the power, it'll be 3x to the 3/2, and then you need to divide by 3/2. And the other one, keep the negative 5 as it is, apply the same rule to x to the negative 2, right? Add 1 to the power, you get x to the negative 1, and divide by negative 1. So you have negative 5x to the negative 1 over negative 1. Now we need to clean this up a bit before we plug in the limits. For example, 3 divided by 3 over 2. You can write as 3 times 2/3, right? And 3 times 2/3, the 3's cancel, so you're just going to be left with a 2. That's how I got this 2 here, times x to the 3/2. And these two negatives will give me a positive, basically. And 5x to the negative 1, bring that x to the negative 1 to the denominator. So you'll have plus 5 over x. At this point, we're ready to plug in the limits. We have done the integration, we have done the simplification. So plug in a 4 everywhere you see an x. And how do you simplify 4 to the power of 3 over 2? When you plug 4 in for x there, okay, remember that that's root square root of 4 raised to the 3rd power. Square root of 4 is 2, 2 to the 3rd is 8. So you're going to simplify that as 8. Okay, so plug in a 4 everywhere you see an x, minus plug in a 1 everywhere you see an x. And simplify. So this is 8. 8 times 2 is 16. Plus 5/4. And then 2 plus 5 is 7, but don't forget the minus sign, so it's minus 7. And you can combine the whole numbers first if you like, such as 16 minus 7 to get a 9 plus 5/4, and that will give us our final answer of 41/4. So the technique really is much simpler, but yet there are still little intricacies, things that you have to learn through many practice problems. So I would recommend that you go now solve as many integration questions as you can, especially all the ones that were assigned in your homework assignment. And in the next segment, we're going to look at area that also involves positive and negative regions, some properties of integration, and a few applications of integrals such as average value and net change theorem. See you next time.